All right, this is the last video on Chapter 8. It goes through just some liquids, as well as it'll be the sections on solids. So it's just a few slides, okay? The first thing I want to mention is that liquids do have an equilibrium process with their corresponding gas vapor. Okay, so they're constantly in equilibrium. In this example here, in the image on the left, shows bromine in a liquid at the bottom of the beaker, and if you see, it kind of actually is sort of floating up into the gas and has sort of a reddish vapor, and oftentimes you can use those vapors for certain things in the lab in certain experiments. But that vapor has a corresponding vapor pressure. So that pressure is in equilibrium with the liquid. This graph from your book shows temperature on the x-axis and vapor pressure in millimeters of mercury on the y-axis, and then just three different substances, and it generally shows, as you see, like even the blue line for water, an increase. As temperature increases, there's going to be more gas and therefore a higher vapor pressure. But even in the lower half, this lower region below the dotted line, you can see that there is a corresponding pressure in this equilibrium between the liquid and the gas vapor before you even actually get to the boiling points, which is this horizontal dotted line on the graph. Okay, so at that point, yes, you're going to have even more vapor to add to the pressure, and that's why the pressure continues to increase. Okay. One of the ways we describe liquids is you can say liquids have, and if you see there's dot, 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 they kind of have two components that are properties of liquids that you're not going to see in, say, gases or solids. So liquids have viscosity, and that basically means the ease that molecules move around due to intermolecular forces. So for example, like liquid water sloshes around easily, you can spill it more easily than, for example, molasses. If you've ever heard the expression, slow as molasses. So molasses is really thick, like tar. So it's gonna be a very high viscous liquid, have a high viscosity, whereas water is, that we are more familiar with, water has a very low viscosity. Liquids also have surface tension, and this is what allows it to form droplets, like you see in this image here, because there is an interaction among the molecules in the liquid because they're closer to each other, and that creates a little bit of tension, which is why you would have like an edge that forms this droplet. Okay, the resistance there that prevents it from fully spreading out. And of course, some substances in the liquid phase have more surface tension than other substances. And so, for example, like water does have some surface tension, and that's what's allowing like the insects that you can see sometimes to walk on water. That's also, if you look at water in a thin tube, it has that shape, that meniscus shape that you are reading in the lab, and you always read the bottom of the meniscus. Okay. The fact that water is kind of climbing up the edges here, I'm sort of exaggerating my meniscus, that is from surface tension. Okay. So solids, there's several different types of solids that we're going to go through, and you need to know the vocab names and kind of the differences among them, and the last slide will just be a table that goes through all of them. It would make very easy multiple choice questions and some kind of assessment. Okay. The first is a crystalline solid. So some solids are crystalline, they have kind of an order to them, and some of them are amorphous. They have a little different structure. There's not a crystalline structure for that, okay? So crystalline, you're thinking of some of these sort of pretty solids that you might be able to buy at the store or something like that, and they're in some form of ordered arrangement, okay? So those are just solids. Now if you have a metal, just metal on a periodic table, you could have what's called a metallic solid, okay? And basically it's just a vast solid with a bunch of metal cations immersed in a sea of electrons, okay? So you would just remember solids are closely packed together, so you could think of it like the cation charge is positive in the middle, and then we just have electrons everywhere. It's like an electron sea is literally what it's called, okay? And the electron C is the glue that holds the cations together, okay? If you were to like jab this metallic solid, the electrons just adjust to a new distribution, so the whole thing isn't going to fall apart, okay? It's all uniform throughout the whole solid. And that's hence why it's its own special metallic solid. Okay, so the next solid is just an amorphous solid that has no defined crystalline shape. Okay, so they're randomly arranged, no long structure like the metallic solid and crystalline solid did. Okay, so this will happen when liquid cools before there's some kind of internal order to the structure. Okay, some examples, some hard candies are actually amorphous solids, but glass, tar, opal, those are all amorphous solids when they're once they're in the solid phase. Okay, excuse me. Amorphous solids often they'll soften over a wide temperature range, and then they can actually shatter. That's why it's like hard candies shatter with curved rather than planar faces. Okay, so those are amorphous solids. Your book has a really good table. It goes over some more, like a covalent network that I didn't go over. It goes over the smallest unit, sort of the forces you might see in there, some of the properties, as well as some examples. So whenever I show you tables like this from your book, these would make great resources to compare and great resources for multiple choice questions, just easy assessments. There's the amorphous solid that I did go over, okay? So thank you for listening. That was just the last part of Chapter 8 that I wanted to go over.